Very good. So we start with the Fourier transform. So we will extend what you know from the Fourier transform in one dimension. We will extend it to two dimensions. So the Fourier transform, I think there are several entities related to Fourier. So you have the Fourier series of continuous signal, the Fourier series of discrete signals, the Fourier transform, continuous and discrete signals. So you have four things called Fourier. So what it says in general, disregarding of whether it is continuous or discrete, what it says is that any signal can be decomposed in a sum of signs, and these signs you have to control a few things. So you have to control the frequency, the wavelength of the sign. So this one is low frequency, this one is higher frequency, higher and higher frequency. So you have to control the frequency. You have to control also the amplitude, so how large the sign is, and also you have to control the phase, so whether it moves to the left or to the right when you have to add them. So for instance, for this square signal, the Fourier series, this is Fourier series, not Fourier transform, but the Fourier series, what says is the Fourier series is when this square signal is repeated periodically. Okay, so what it says is you have a sign, and this sign has a frequency, so the frequency is controlled by this term. Then it has a phase, but the phase is all the time zero, so that is why it is not written there. And then it has some amplitude, so the amplitude is this one. Okay, and if you add all these lines, what we have is an approximation to the signal, and if you add infinite signs, then you have an exact representation of this signal, except for these discontinuities. So this you already know. All of you know the Fourier transform? Yeah? Okay, good. Okay, so these are called the sinusoids. They're called the basis functions, and they will play the same role as when you express a vector as in a coordinate system. So somehow this is the coordinate system in which you are describing your signals. So those are the Fourier coefficients. So the amplitude and the phase is also encoded there somehow. And when we use the complex exponential as the basis, it is more clear that the phase is there in front. Then, so here you have an example of how by adding more and more sinusoids, we are getting closer and closer to the signal you want to represent. So this is with just one Fourier coefficient, with 2, with 4, 8, 16, 32. And these are overshooting in the approximation is caused by the discontinuity. Do you remember the name of that? The ripple and Gibbs effect. This is the Gibbs effect. And Gibbs written like this. Written like this. Gibbs effect. Okay. Very good. So then, as we said, you have to control a few things: the amplitude, the frequency, or the period. Those are equivalent, and the phase. So the phase is whether you should move it to the right or to the left. So this one has a positive phase. If you put phase equals 0, then this point would move to here. Very good. So, yeah, and there are a number of names. So 1 over lambda is called the frequency. It is measured in hertz. Hertz is 1 over a second. 2 pi over lambda is called the angular frequency, and it is in radians over second. Lambda is the wavelength. It is not there, or the period, and it is measured in seconds. Okay, then let us introduce some vector notation. So let's say that functions are also vectors. They're also vectors. So there are vectors in some vector space of functions. So if there are vectors, you can compute the inner product between two vectors. So how do you define the inner product between two vectors? It is the inner product between the function f and the function g is f times g complex conjugate, and you have to integrate in some, if both are periodic, you have to integrate in the period. So from minus lambda half to lambda half. And it doesn't matter if it is minus lambda half to lambda half or 0 to lambda. Well, as long as it is a full period, you will get the same product. And if this is the inner product, two vectors are perpendicular to each other, if they or orthogonal to each other, if the product is 0. So if the product, this product is 0, then the two signals are, or the two functions are orthogonal to each other. So here we would have a representation of that inner product. So let's say that you have f, and then you want to know if this function g that is in blue is a component of f. So it's a component, it is inside. So to reproduce f, you need this g. Okay. So if you need that g, that would mean that the inner product between the two will not be 0. If you don't need it, then it will be 0. Okay, so I have to compute the point-wise inner product f times g. This g is a real valued function, so g complex conjugate is g, so we don't write it. So you have to multiply point by point f times g, and the red one is the multiplication. And then you have to integrate from minus lambda half to lambda half. So you have to compute all that area. And all that area, okay, we cannot compute by eye, but you see, okay, more or less these are ripples of the kind of the same size. So the integral in this area will be a number very close to 0. But we see that there are some regions with very positive numbers. So that there is a, the integral is positive. So just by eye, it is positive. So this is g is a component. Okay. We will see component in which way. Okay, let's say that we also wonder if this h, now it is another one, if it is a component of it. So you do the same, you multiply f times h, that gives us the red curve, and then you compute the area, and now the positive and negative areas, they compensate each other and the product is 0.
Is 0, that means that function is not
A component of, yeah. Before going to these inner products between functions, let us reason why, if two things are independent, are orthogonal, if two vectors are orthogonal, then we say one is not a component of the other. Okay, so let's say that I have a vector. So I have a vector r that is x, y, z. Okay, so what does that mean? So that means that in this vector space, that I will call it E1, E2, E3. So these are the unit vectors in each one of the direction. I have some point that is x, y, z. Okay, good. And this you already know that I can write this as x E1 plus y E2 plus z E3. This you know, right? Okay, but this I can also write this way. So I can also write this way. So what is x? X is the projection of the vector. This is vector r. So it is the projection. Let us draw the projections in purple. So it is the projection of, so I can this. So this is x. So it is the projection of the vector r onto E1. So I can write that this is r times E1 times E1 plus R times E2 times E2 plus R times E3 times E3. Very okay. And now let's think of a particular vector. Okay, so let's think of the vector R equal 7, 0, 2. Okay, so that is 7 times E1 plus 2 times E3. So now we observe E2 is not a part of R. It is not a part of R. Right? And also I say this is 0 E2 plus 2 E3. So this 0 is because R times E2 is 0. So these two vectors are orthogonal. Okay. So in that case, the R that I have written is this correct one, belongs to this plane, belongs to that plane. And if you belong to that plane, any one of these vectors is orthogonal to E2. So we say E2 is not a part of R. It is not a part of R in this sense. They are orthogonal. So to reproduce R, I don't need E2 in any way. Okay. Very good. So then, I think this presentation here in which it's first presented with sines, cosines, and all that, I find it quite confusing. So I will go directly to complex exponentials. That is the definition of the Fourier transform. Okay, so then we go back to this representation. So let's consider this representation again. So what it says is, if you want to represent a vector in some basis, this basis, what you have to do is the multiplication of that vector times E1. E1 and it is a particular case. Okay, so we will extend this one. But yeah, E1. So you have to multiply this by something related to E1 and multiply by E1, and the same for the others. So in general, the most general formula would be something like this. If you are in n dimensions, and you want to represent the vector R, so what you have to do is the sum over all elements in your basis. Ri and multiply by EI. What is special is that actually this is a particular case for R3. In general, you have to multiply by something called the dual. So this is the dual basis of EI. And then what is special is that in the Euclidean space, the standard basis is the dual of itself. So the multiplying by the dual or multiplying by the basis itself is the same. But in general, this is not the case, and it is not the case of the Fourier transform. Okay, so what does this have to do with the Fourier transform? So let's say that I have a signal T on x of t. Let's make this signal for the moment periodic so that we can use sums. So this signal is periodic, let's say. And we will focus in the period 0 to 2 to lambda. Okay, so this is lambda, we will concentrate there. And I want to express this signal in some basis. Okay, so why don't I do the following? So choose a different color, this one. So why don't I use Dirac deltas represent many of those deltas. But then what I say is, okay, this one is, so each one of the deltas is T moved to some position tau. Okay. So I look at particular position tau, and then I put, so I will collect all the deltas. So what I have to do is, this is the sum. Let's write sum for the moment. The sum for all deltas of x at tau multiplied by delta t minus tau. Would you agree with that? So this is what it's saying is, for every tau, look how much is x of tau, and then you have to multiply times the delta moved to that location.
So that is linear convolution.
Exactly. I want to get to a convolution. Yeah. So what happens? This tau is continuous. So you shouldn't sum, you should integrate. So you should integrate. So you should integrate over tau. Now this is correct. And this you already know, this is the convolution of Z. And this is one of the trivial properties, right? So x of t convolved with delta t is this thing. Okay, but now let's look at this. What is this? This is the inner product between x of t and delta t minus tau. It is that inner product. So what we are saying is x of t is an integral and a sum is the same. Okay? So it is the integral. Let's make Fourier real space red. It is the integral over tau of the inner product between x of t and delta t minus tau. Delta t minus tau differential with tau. So this is E1. This thing is EI or E tau in this case. This is E tau again. Okay, so when we write x of t and we think of it as a collection of delta functions, it is writing this thing. So all this is a basis in the same way as these were a basis. So these coefficients here, or these vectors here, these vectors there are bases, and these are the coefficients. These are the coefficients associated to those bases. So here we have the same structure. So we have a basis. We have to sum over all elements in the basis, and then we have to multiply by the coefficient associated to that basis. Okay, let's look at the Fourier transform now. So I have said these delta functions are a basis. So the set of bases is the delta functions. Right. This this is delta t minus tau for all tau. For all tau that makes sense. If your function is periodic, the tau that makes sense is from 0 to lambda. Okay, now, very good. So now let's write the Fourier transform. So the Fourier transform, then let's write the inverse Fourier transform. So let's write the inverse Fourier transform. So the inverse Fourier transform says, this is the integral of frequencies of, which one is more convenient to write? x of j omega, then this frequency is omega, and then E plus j omega time differential of omega. Okay, so let's compare these two. So now we say, okay, this set of functions is my basis. So it has the same structure as this one. So it is something. So the key here is that they depend on time. So it is some functions that depend on time and something else. So this one depends on time and something else. So this is my basis. So this is my basis. And if this is my basis, let's use the same color. This is my basis. And if this is my basis, this is the Fourier coefficient. So it is the same kind of coefficient that we were having here. So it is how much you have to multiply this to recover the original vector. And then this has to be the inner product between the two. So it has to be, so if this is true, this is equal to the inner product between x of t and the basis function. So what is the inner product according to us? It is the integral, and this integral is over time of x of t times e to the minus a omega and differential of time. Right? Because this is the basis, and we said complex conjugate. So when we wanted to compute the inner product between two functions, the second one has to be complex conjugate. The complex conjugate of e to the j omega t is minus j omega t. The complex exponential you all know, right? Okay, very good. Okay, so and this is the dual. This one is which color to use? This is dual. So here is dual. Meaning is dual. Okay? It is the dual of the delta, and it is also complex conjugate. In our definition, it plays both roles. Actually, it is not by chance that we use the same symbol for both, for dual and for complex conjugate. Okay, so it is the same. So my vector is some Fourier coefficient. This Fourier coefficient is an inner product times my basis. And this inner product has to be with the dual of the basis. And for Euclidean space, the dual of the basis is itself. But in general, it is not. And for the delta functions, it is also itself. Okay. So this is very nice. Yeah, so if this is the reconstruction formula, this has to be the Fourier coefficient. The Fourier coefficient has to be the inner product between the two. And this is just the definition of the inner product. So x3 e to the minus the negative. Actually, this one is also the dual of its itself. They are not dual if they are not orthogonal, but all these ones are orthogonal to each other. Which one? Here, this one. Yeah. Because the definition of the inner product has a complex conjugate. Okay. Very good. So the Fourier transform is nothing more than a change of basis. So now we have a few bases. So we have real space. Real space is the basis of delta functions. And Fourier spaces, the bases are these complex exponentials. And then here is what I said. These numbers, you know that they are complex. Okay? So this integral in general will be a complex number. If it is a complex number, then it has, let's call it x j omega. And here we see the notation shows this depends on omega. So it depends on omega. That is the argument. It is the same role as tau here. So it is the argument that somehow modifies the basis function, chooses which basis function you want. So here, the one that chooses which basis function you want is omega. So this coefficient depends on omega. So it is a complex number. So this is complex. It's a complex number. And if it is a complex number, then it has an amplitude and it has a phase. Here we write it like this. So we say it has an amplitude, that is the module of x in that. And then it has a phase, that is j phase of x limit. So this is A, this is A, this is phase, this one is phase. And all this is for one-dimensional signals. All this is for one-dimensional signals. We haven't started yet with images. Any question up to here? No? Okay, very good. Then, so this presentation with couple of signals can be done also that way, but I find it more confusing. I think it is more clear if you directly use the complex exponential. And in my notation, this is capital omega. So his little omega and my capital omega is the same, and it is 2 pi divided by lambda, by the wavelength.
But you're saying that they're both the same.
Yeah, yeah.
Is just one supposed to be normalized?
This one,
No, what we've seen in biomedical signals
Yeah.
is that the big one, the capital omega, is a normalized one.
yeah. So it depends a lot. There's so many Fourier transforms, and so many ways to define the Fourier transform. So you may define it depending on the context, okay? But depending on the context, so omega is typically used in signal processing. It is used for continuous signals, and it is measured in radians per second, and the exponential term is this one. But then you have it also frequency. Then it is also continuous signal, but this is 1/2, and the exponential is this one. And when you use this one, the small one, typically it is for discrete signals, and it is measured in 1/something. 1/something. And then you have this one. So it is a typical use, but it depends on the author who is writing. So, but the concepts are the same. So if they represent frequency, whether they are normalized with 2 pi or not or whatever, you don't care. So it is the frequency. When you care really a lot about the details, then you have to care. But for the concepts, you don't. Okay, whether they are normalized, if it is discrete or it is continuous or what. Very good. Yeah. So in his notation, if you look at the formula, his formula is using omega and normalization. So his small omega is my capital omega. So actually, do you study with the Oppenheim book, right?
Yes.
Yeah. So in the Oppenheim book, this is capital omega. It's my same notation. Okay, very good. So then, yeah, we skip all this part with two bases, sine and cosine, all that we skip. Yeah, all that we skip. Yeah, again, here it is having the two bases, the sine and the cosine, and then the phase gets all this complicated. So it is much more, it is much cleaner to use the complex exponential that is actually the one that is normally used for the Fourier transform. And then the phase and the amplitude both go into the coefficient, the Fourier coefficient. Okay, then all this is the same. All this, we can speak for that. Okay. Actually, this is very interesting. Our senses are sensitive to signals in the real world. So what about sound, for instance? So sound, we know it is a signal. And what you can put here is the sound pressure. So if you plot the sound pressure over time, so it is pressure over time, and then it has some low pressure and then high pressure and then low again and then high again. So it cannot be negative. Okay, so the pressure cannot be negative. So the wave, so the oscillations can be negative. So the oscillations here can be negative. Okay, but the pressure itself cannot be. And then you can decompose that. It is a signal, so you can decompose it in amplitude and frequency and phase. And what turns out is that we are insensitive to phase. So we can only hear the amplitudes. All the phases, we are totally blind or blind to the phases. And it is something that you can try on your computer. So you can record your voice. So you have the signal, you do the Fourier transform, you randomize the phases, and you do the inverse Fourier transform, and you still listen the same. Okay, very good. And then you have the discrete Fourier transform. Okay, so the discrete Fourier transform is for not continuous signals, but for discrete signals. Okay, let's make some drawing here. So we have x of t. So this is still continuous, and we have x, j, n. This goes in the Fourier transform from minus infinity to infinity, and here the same. T goes from minus infinity to infinity, and you have some spectrum. We normally represent like this, right? So these kind of representations you are used to. The important thing here is that this one goes to infinity. Okay, so if x is continuous, if x is continuous and non-periodic, then that one goes to infinity. Okay, what if my signal is continuous, but it is periodic? Okay, so let's represent it that way. It is not a sign, but something that is periodic. So how is my spectrum? My spectrum is a set of deltas, right? And it has to be symmetric. But it still goes from minus infinity to infinity, the frequency. Okay, now I have a continuous signal, a discrete signal. So now I have a discrete signal. So I have something like this. Or x of n. This is n. How is my Fourier transform? So now I have to define now my Fourier transform, because this one we have already defined. This Fourier transform is the one we have just presented. The inner product between your signal and the complex exponential. See, I'm more used to write a small omega. So it is this integral from minus infinity to infinity of x infinity. Okay, but now my signal is discrete. So how do I define the Fourier transform? So I will put already the result. And then we will define it. So the result, it is something periodic. I will call this frequency axis a small omega. This is the, and this is in the notation of the Oppenheim again. You have studied this notation, right? No? Yeah. So it is this one, and it is periodic. It's periodic every 2 pi, and here at minus 2 pi, it is a periodic this thing. Okay, so how I define this? And this is for discrete. This signal is discrete and non-periodic. Non-periodic. Okay, so how do we define the Fourier transform for these signals? So it is x into omega will be the inner product between x of n and my basis function. But my basis function now will be this one. But it's almost the same as the other one. And I have to define the inner product. Okay, so the inner product is defined for 2 discrete signals. Defining in this way. So now, because they are discrete, it is not an integral, it is a summation. And then the rest is all the time the same. Okay, so this will be the sum minus infinity to infinity of x of n into the minus j omega. And this also Okay, and this is the units of this is radians per sample. Very good. And for this one, let us write it for this. The units are radians per second. Okay, good. So then we have only one guy missing. That is what happens if this signal is periodic. This signal is periodic. Let's say it is this one. Or it is trying to represent something that is periodic. You do the Fourier transform, and then you have this kind of a spectra that is periodic. I will not draw the periods. But actually, this one is a kind of envelope, because the true Fourier transform, I will draw it in red so that it is more clear. The true Fourier transform is a set of deltas. And the separation between these deltas has to do with the period of x. So this is the period and how this is related to that period. It's 2 pi divided by n. Any question up to here? So this is a reminder of everything you know from one dimension. Okay, good. Now let's go for images. So yeah, here you have say this is the forward Fourier transform. We have a signal This is the forward Fourier transform. This is the inverse Fourier transform. Actually, I would have changed the minus here and the minus and the plus there. So depends on what you say is your basis. But if your basis is +1, that is the typical one. So here putting plus, not minus, then you have also to change those signs. Okay, but so how do we extend to higher dimensions? So we have to define, yeah, that is something else that we should also say. That is, all these bases are orthogonal. Okay, so they are orthogonal in the same way as these ones are orthogonal. Okay, so let's go back to vectors that you are more familiar with. So if I compute for these bases, we compute E1 times E1. This is 1. E1 times E2 is 0. E1 times E3 it is 0. So this means it is orthogonal, or it is an orthogonal basis. And this one says it is a normal basis. So normal basis means that the norm is 1. Okay, so this means if I multiply a basis by itself, I get 1, or I get a number. If I multiply a basis by any other basis, I get 0. So what about complex exponentials? It is the same. So complex exponentials, they are defined by the frequency. So if I compute this one times any other one, I get 0. And if I multiply 1 by itself, I get a number. Raised to pi, I think. It is in the slide. If you go from minus infinity to infinity, you get infinity. But if you go for one period, you get to pi. What else? And the same happens for these ones. Okay, for the basis functions of the discrete Fourier transform, it is also if you multiply two that are different, you get 0. If you multiply two that are the same, you get some constant. And that's all. I want to say something else. Yeah. We discrete Fourier transform, or discrete Fourier transform, you see that this 2 pi divided by n plays a role because it is the difference between two samples. So you see that it has defined the basis function for, or the basis set for the discrete Fourier transform as 2 pi divided by n times k. Okay, so that means that this is the, sorry, this delta is the one that you get for k equals 0, this for k equals 1, this for k equals -1, k equals 0, so on. Okay, so k is the index of your delta. Very good. Any question up to here? No? All this you know from one-dimensional image processing, signal processing. Okay, now let's go for 2 dimensions. And again, for 2 dimensions, I think this is fine, but I prefer some other notation, which I find it more convenient. Okay, so now let's extend this to more dimensions. So instead of so we have an image. Let's do it first continuous. So we have our image here. So R is X I. And then you do the Fourier transform. So the Fourier transform will be something. This is less common to use the J here, but okay, so let's try to keep the same analogy with one dimension. So this is a vector, 2D vector. So this is a 2D. So now we will, instead of having one frequency, we will have also two frequencies. So this is I omega X, omega Y. So now instead of having one frequency, we have two frequencies. And this one I cannot draw. Let's say it's omega Y, omega X, and there is some function here. So let's say it's kind of the same triangles we were plotting before. Okay, so now how do I define my basis? So my basis, what was it before? Let's so before the basis were this color, but the basis was this one in one dimension. One dimension was this. So now I have to do something that is kind of similar to that. So it will be this one. So this is an inner product between a frequency vector and a spatial vector. And here it is the same. It is the inner product, only that I have only vectors of one component between the frequency vector and the time component. So this is time, this one is time. In images, this one is a space. But otherwise, everything is the same. And because this was time, omega, you remember it was radians divided by sample, by second, right? This one, the units of this will be radians divided by meter, because it has to be the opposite of space. Here it is the opposite of time. Time is seconds, so this one is seconds. And now space is measured in meters, so it is radians per meter, or radians per angstrom, so per millimeter, or whatever space distance you want. And then these you can also express as J, and then omega X. So we multiply, it will be omega X X plus omega Y Y. And this is the kind of expressions that he has in the slides. He's putting in front 2 pi. We don't care about the 2 pi. So we absorb the 2 pi in the frequency component. So it will be 2 pi, or forget about the 2 pi. Frequency in X times X plus frequency in Y times Y. Okay. And for so this is for the discrete signal, for the continuous signal. For the discrete, we will define it in this way. So 2D, this is 2D continuous, this is 1D continuous. And for the 2D discrete, we could define it this way. Omega R, or omega N, if you want, N. Or you can also define it, this is the same, it depends on what is the definition of your thing. You can also define it this way, as he has done. Okay. So this K has the meaning of Kx, Ky. In the same way as we had here different Ks. Okay? But these Ks were in one dimension. Now we have two Ks, one going in X, another one going in Y. This is your basis function. Now we already know how to do Fourier transforms because we already know. So for instance, let's say that I want to compute this Fourier transform that we have here. So I want to compute the Fourier transform of an image. So I know it will be the inner product between my basis, and my basis is this one. So that my image, let's put my image first. My image and my basis function, but my basis function is this one. This is the forward Fourier transform. If you want, we can expand this, and we can say this is the integral over all space of image times E minus J omega R differential of R. Now I have my Fourier transform. How do I reconstruct? So to reconstruct, I simply have to collect all these coefficients and say my image, real space will be my integral, but now my integral over all frequencies of my Fourier coefficients times my basis. Now differential of frequencies. So I have to sum over all frequencies, take the basis, this is the basis, multiply by the Fourier coefficient in front, and then I reconstruct my full image. Okay. So this is inverse Fourier transform. This is inverse Fourier transform. This is forward Fourier transform. Time for a break. So let us make a break. So this slide is simply saying we have orthonormal bases. So orthogonal bases. So the product of two waves of different frequencies, it is zero. If the frequencies are different, and different from zero if they are the same. And these are the 1D versions of that. The same happens with 2 dimensions. Depending on whether you go from minus infinity to infinity or from 0 to 2 pi, this is infinity or it is 2 pi. And for this discrete Fourier transform, or this discrete basis for the Fourier transform, in which you have the indexes, and here the indexes, they are called J and K. I think it is more clear Kx, Ky. And the same here. N for me would be Nx and Y. Here for him it is M and N. So the problem with J, K, M, and N is that you never remember in which direction they're going. So you put the subscript, it's more clear. So then we can define the Fourier transform. So the Fourier transform is the inner product between the two. In my definition of Fourier transform, this is minus, this is plus. For him, it is the opposite. It depends on what is your choice for the complex exponential. So he has chosen the minus, a complex exponential with minus, and I choose it with plus. So this is the inverse Fourier transform. This is the This is the inverse Fourier transform. This is the forward Fourier transform. And the same for the discrete ones. Okay. Yeah, more representations of these formulas, right? Okay, so this is the inverse Fourier transform. So here is the Fourier transform coefficient, and you multiply by the basis, and then you have your input image. And this is, so sometimes this is called the synthesis equation. This is called the analysis equation. So the analysis equation is, I take my image, I take my signal, and I decompose it in my basis, that is analysis. And the synthesis is, I take all the components of that signal that I know from the coefficients, and I put all of them together, and that is called the synthesis. And the same for the discrete ones. So the discrete ones here, these torus, I think it is another way of looking at the Fourier transform, but I think it is not so easy to see. Okay, so let's forget about the torus, and here we have the forward and the backward and the inverse Fourier transforms for discrete images. So now this one is discrete. In our notation, we know discrete has a square brackets, and then this is the inverse Fourier transform. Okay, very good. So yeah, this is rather repetitive. All these formulas, they don't introduce new ideas. Okay, so this is a new idea. So we have talked of complex exponentials in 2 dimensions. So actually, this one is a little bit better in the sense that what if my images are not a square? So if they are square, let's say that my image is n times n pixels, then this is quite consistent with the indexing that we have. But what if my images are not a square? So they have independent number of rows, number of columns. Then the right way of normalizing is this one. You recognize here, you recognize the inner product. So this VR is an inner product. This you see is an inner product. If you want, you can put it also this way. So let's extend this one to be for non-square images. So for non-square images, you can put it this way. It's a basis of 2 pi, and kx divided by number of rows, ky divided by number of columns. This is a vector times your index. So it is the same. So this is the right way if your images are not square. Very good. So then we have this kind of complex exponentials. What do they mean? So let's define a few things. So we were used to have a frequency. Okay, so let's look at the concept of frequency here. So a frequency. So in general, this would be this omega x, omega y. Okay, so let's do it in our notation. In our notation, what we are looking is at this. So in our notation, what we have is I try to make same to what Ash is doing. So I have omega y, omega x. I have a point here that is my frequency, that is a vector. And I want to understand what frequency is that. So this is what he's doing here. Okay, so it's the same plot. So this is the x component, this is the y component, the opposite. This is x, this is y. And then I can define the module of that vector. I have the module of that vector, and I have the tangent with the angle with x. Okay, so it is the arctangent omega x, omega y divided by omega x. Okay, I have the module. So we are used to a sinusoid to have a wavelength. Okay, what about the wavelength? So the wavelength, now these formulas are only valid for square images. So it is n divided by this module. And what else? This you can skip. But you know, what is important here is that a complex exponential is cosine. So it is just a reminder of this formula. So e to j omega is cosine of omega plus a sine omega. So this is what we have. So we have e to the j prime something. So it will be the cosine of that something plus minus of the j. Of the j, yeah. Plus j, and then the sine of that something. So we have a vector frequency, and that vector frequency will have a module, and the wavelength will be related to the module. And then we will look into the real part of these complex conjugates. Okay, so these complex exponentials, because a complex function we cannot draw. So we can draw the real part, the imaginary part, but not both together at the same time. So let's concentrate in the real part of it. So if we concentrate in the real part, so in general, we will have so we are reconstructing. Let's reconstruct our image again. Reconstruct our image, and it is now I will go discrete. So this is the sum over all frequencies, and the frequencies for us they were k. It is the sum over all frequencies of the Fourier component for that frequency. Let's call it. Let's call it. So the hat is also Fourier transform. When you put the hat, you are in the Fourier space. When you don't put the hat, you are in real space. And it is a value of k. And then my basis. Basis, that is this one, by n, k, n. Okay, but this is a complex number. So this one here, this one is complex. So if it is complex, then that means that it has an amplitude and a phase. Phase, let's call it like this. Times this thing. So times my basis. E to j to 5 k divided by n. K n. So I can put these two complex exponentials together. So it will be sum over k, or the module k. 2i sorry, n plus And now we take the real part. Take the real part of that. So it will be the sum, okay, of this is real, right? So this I don't have to change. Then I have to take the real part of that. So this cosine of 2 pi and so what is important here is that we have the frequency. So we have cosine of frequency and phase. So frequency and phase. Okay, so that is what we are seeing here. We have cosine of the frequency plus phase. Okay, and this comes from only studying the real part. There are no considerations there if we want. But if my image is real, the Fourier transform, you know this from again from 1D signals. So let's put it from 1D signals. So if this is real, then Fourier transform fulfills this property. So you know this property, right? This is called the Hermitian symmetry. Symmetry. So for images, it is the same. So if your image is a real image, so if you have a real image, then the Fourier transform of your image, the omega, is the same as the Fourier transform complex convoluted J. And then if this is true, instead of having to take the real part, what I can do is take the one coefficient, the one that is symmetric, add the two, and then I will have a cosine. Very good. But what is important here, studying the cosine of the complex exponentials associated to those frequencies, it is important. Okay, so now let's see some concepts here. So what is important in the sinusoid? You have an amplitude, you have a frequency, and you have a phase. Okay, so what is the amplitude? So this is how a 2D sinusoidal looks like. So it is a sinusoidal. In one direction, it is sinusoidal. In the other direction, it is flat. It's constant all the time. Then what is the amplitude? So the amplitude is the contrast between the minimum point and the maximum point. And what is the frequency? The frequency is associated, so the inverse of the frequency with whatever factors we need of number of n, 2 pi or whatever. But this is the separation. The frequency is associated to the wavelength, and we have the formulas for the wavelength. So formulas for the wavelength we have them here. Okay, but you don't care about n or whatever. The important is wavelength is inverse frequency. So it is the separation between two equivalent points. So to maximum, to minimum, whatever. So here we have marked two maximum. So if I have low frequency, I will have large wavelength. So if I have low frequency for one of the sinusoids, the wavelength will be very large. So this becomes very smooth. And if I have high frequency, this will become very quick. Okay? It compresses. But now there is something new because we have a frequency vector. We don't have a scalar frequency. So you have a frequency in X and a frequency in Y. So what they control is the orientation of this wave. So this wave propagates in the direction omega. And what is the angle of this omega? The angle of this omega is given by the angle of your frequency vector. Okay, so do you remember? Yeah, and let's put the phase now. Yeah, so we have a frequency vector. So a frequency, the vector, the orientation of the vector tells you the direction in which the wave is propagating. And we have a phase. So if we have a phase, that was if it was starting before or so earlier or later in the time axis. So it is in the propagation axis. Okay, so when you change your phase, this wave will move forward or backward, but in the propagation direction. That is the phase. So let's remind our statement at the beginning. So at the beginning we said Fourier transform says that any signal can be represented by waves in which you control the amplitude, you control the phase and the frequency. So what we are saying is any image, any image can be represented by a sum of waves in which you are controlling the amplitude, that is the contrast. You are controlling the frequencies, so how packed they are or how spread they are, and you're controlling the phase. So we are adding waves, a lot of waves of this kind to get any image. And here we have an example. So we have this image. Let's put it in, you can do this analysis for the 3 channels. So the Fourier transform is something that is defined for scalar images. So if you have a color image, you decompose in the 3 channels. Here we are showing one of them. So you do the Fourier transform, and what we are representing here is the frequency. So this is the 0, frequency. And then for each one of the different frequencies, you compute what is the real part and the imaginary part. And that is what we are showing.
What happens if you repeat both?
Sorry, say that again?
Like with the frequency vector,
Yeah.
what happens if you that image rotate? If we rotate also
If you rotate the image?
no, like the frequency vector.
Okay, so I have a vector. So this vector is pointing in one direction, and now I rotate that vector.
Yeah.
Okay, so then I have a different frequency.
And you will have like the same image back rotate.
No. One thing is rotating the image, another thing is rotating the frequency. So the frequency, it is like you have a, let's think in images, but in real space. You may be not familiar. So I have this image here that is I of R, and R means that if I look at this R, I have a value that is I of R. So one thing is rotating the image, another thing rotating the vector. So I may rotate the vector and look at the image somewhere else. So it is the same in frequency. So one thing is considering a different frequency. So I'm looking at this frequency and I have some frequency value there, or some Fourier transform value there. I rotate my vector, so I'm looking somewhere else. Okay, it's the same as in here. So you may rotate the vector, or you may rotate the image. So those are 2 different operations. Okay, so I can look at the real part and imaginary part. But then, so now let's think a little bit more about frequencies and wavelengths. So we had a frequency vector. So this frequency vector has some angle and it has some module. But I can also look at the, I could also define two associated frequencies. So I have two frequencies, omega x, omega y. So omega x, omega y. This u and v for this in this slide, they are the k's. Okay, so they are indexes. So k x value 0, 1, 2. They are the indexes of the different Fourier components. And then I may wonder what is the overall frequency in the direction of the wavefront. So in the direction of the propagation of the wave, it is this thing. What is the associated wavelength? It is this one. And I can also, these are frequencies. So if I invert them, I have some also wavelength. So what is the meaning of all this? So let's look at again at this wave that is propagating. So the overall wavelength in the direction of the propagation of the wave, it is this one. What is the distance between two equivalent points? But then, yeah, here. But then I could also look at the x and y axis. So in the x and y axis, I have also some frequencies. So I have these are indexes, okay? So this is the index kx, index ky. And we have associated two different wavelengths to x and y. So what is the meaning of those wavelengths? Let's look at the x and y direction. So in the x and y direction, so in x. So in x, I see that it oscillates this much. In y, it is oscillating much less. Okay, so these waves induce an oscillation in x that is different from an oscillation in y. By how much and what is the relationship between the two? It has to do with the propagation direction. So it has to do with let's see here. So in the direction of the wavefront depends on these two indexes, and in x and y it depends only in the one index and on the other index. So the angle between the two somehow combined here. Okay, then yeah. So here is right. So now we have a real part and imaginary part. But for instance, here we already did. So let us see our drawings of the Fourier transform. So typically, you plot the module of the Fourier transform. So we can do the same with images. So you take the Fourier transform, which are complex numbers, and then you take the module. And in real signals, there is a lot of difference between the low frequency components that may be in the order of 1,000 and the high frequency components that can be in the order of 10 to the minus 3. So there are kind of 6 orders of magnitude of difference, and then you plot the logarithm, because otherwise you cannot see them. And you can represent the module and the phase. These are the real and imaginary parts. Okay. Any question? No? Okay, so now how do we define the power spectrum? Actually, this definition of the power spectrum is a little bit restrictive. So let's give the more general definition of the power spectrum. So let's say we have this image. We have this image, and we will compute the autocorrelation of this image. So the autocorrelation of this image with a lag m is I have a location there, and I look, for instance, at the r plus m. So what happens? So I have a location, what happens in the neighborhood of that location? And that is for all points the same. So if I have this point, then what happens with this? And this for a vertical end, I could study for a different end. Okay, so I could have this R and then this M. Okay, so for an arbitrary vector n, this is the expected value of the image at R times the image R plus n. This is the definition of autocorrelation. So if my image is random, for instance, I have noise, my image is random, then this is the autocorrelation of my noise. And if my image is not random, then this expected value, this expectation, because I is not random, the expectation disappears. So that is why I say the other one is too restrictive, because it is only for deterministic signals. So the power spectrum, I will drop the J. So the power spectrum density at a given frequency, it is the Fourier transform. It's the Fourier transform of my image at that frequency. Now more. These are sorry. Now that my image of my power spectrum density. My power spectrum density. So the power spectrum density, the autocorrelation function is another image. And then I do the Fourier transform of that image, and I get the power spectrum density. And this is where it becomes restricted. If my image is deterministic, I is deterministic, so there is no noise, then this is Fourier transform of the image S2. But only if I is deterministic. So if there is no noise. But if there is noise, this is the correct way. So first you compute the autocorrelation function, and then you compute the power spectrum density. Okay, so what he has here is the definition of the power spectrum density for deterministic images. Then how to compute that in MATLAB. This is something that you already know, this uncertainty relationship. So uncertainty relationship means if something, there's a picture here, yeah. So if a wave is well located in real space, let's put it different. If it is well located in frequency, it will be very badly located in real space, and the opposite. So you already know this. This is a real space, this is frequency space. If I have a wave that goes from minus infinity to infinity, what is the Fourier transform of a wave? It's just a delta. So or a couple of deltas because of the symmetry, right? So I have a couple of deltas. So here it goes from minus infinity to infinity, and here it is just a point, an infinitely thin point. And you have the opposite too. So let's give a few examples there. So let's do it in one dimension, that is easier to draw. So I have a wave, x of t. My Fourier transform is a couple of deltas. So this is x on I don't know. I delete. Okay, so then Fourier transform, this is omega, is just a delta, no vector. We are in one dimension. Now, for instance, what if my signal is a delta? What happens if my signal is a delta? How is my Fourier transform? Still, is my Fourier transform. As you know, no? This omega is a zero. You know that result, no? And this is a wave. So if I draw that, it's a wave. That's constant weight. What if my signal is a constant? My signal is constant. So I have some constant signal. Is the Fourier transform. Always label your axis, okay, when you make it through. It's a delta. It is a delta related to that constant. So if something is very wide in one space, it will be very compact in the other space. It is very compact and it is very wide. Okay, so these are kind of extreme cases, but in general, it always applies. So this somehow is trying to encode. But this is called the uncertainty, Heisenberg's uncertainty principle. So that comes from quantum mechanics, but it also applies to the Fourier transform. And the formula is not this one, but somehow it is trying to say the support of the signal in real space times the support of the signal in the other space has to be larger than something. And if this is very small, then this has to be very large so that the product is still larger than that. So yeah, that happens within these two. So if I have wave and an image, it will be just two dots in frequency. What about this one? This one in this direction, let's look in this direction. So in this direction, it looks like a constant. For all rows, it looks like a constant. So this is somehow has to be related to a wave because it is just 2 points. In this direction, it is 2 points, but in this direction, it is a constant. Okay, so in this direction, it behaves as a wave. In this direction, a constant, we saw already. Constant is a delta. So in this direction, it behaves as a delta. Because it is very wide in this direction, then it has to be very compact in this direction, in the other space. What about edges, for instance? So an edge, in this direction, they behave like constants. So in this direction, they should behave as a delta. And in this direction, it behaves as a step. So step, the Fourier transform of a step is a 1 over j omega. So it behaves like something that decays as 1 over the frequency. What if it is a bar? So if it is a bar, so in this direction it is flat. So if it is a constant, then it behaves as a delta. And in the vertical direction, it behaves as a step function. This step function is a sink, right? So what we have is a kind of sink in this direction. This direction you have sink. This direction you have a delta because this looks like constant everywhere. So this uncertainty principle that if something is compact in one space, it is extended in the other space, now applies in all directions. Any question? So I think it is good time for another break. The following thing that we are going to, is how the Fourier transform is arranged by some routines, and this has to do also with what is the meaning of a given coefficient for a given at a given location of the Fourier space. Okay, so let's come back to one dimension that you know better. So say that you have some signal that has 4 samples, and then it is repeated. Okay, and then on the other side it is the same. So you have this one, this one, and again this one. Okay, so let's look at the Fourier transform of the lag signal allowing. So this Fourier transform, let's put it in omega. So it is a discrete one. Like this. So this is the one that you know that goes from -5 to pi, and then it repeats every 2 pi. And we normally, because these are complex numbers, we normally just represent the amplitude. Okay, so first thing, in this Fourier space, it's the same representing this one or representing this one. That's exactly the same information, right? Exactly the same. Very good. Then we have the periodic signal. So the periodic signal, we know that it is made of deltas. So it will have some deltas. What is the separation between the deltas? So here n is equal to 4, and we said the delta omega is 2 pi divided by n. So it is separated every 2 pi divided by 4. That is delta omega. In this case, it is pi half. So we will have a delta at k equals 0. We will have another delta, let's say at pi half. Let's say it is this one. So this is a k equal 1, k equal -1. We will have another delta at k equal 2. This is k equal 2. And it is 0, but I'm trying to represent it there so you can see it. Now, k equal 2. So what is 0 is the amplitude. So this one is 0. And at k equal -2, that again it is 0. For us, zeros are somehow there. But we know that these two are the same. these two are this is the same as this one, because this is at minus pi, this is at pi, and it has 2 pi periodicity. So these two samples are exactly the same. So we only need to keep one of them. So we only keep these 4, right? 1, 2, 3, and 4. And then you know that if your sample has n, your signal in real space has 4 samples, then in Fourier space it also has 4 samples. But the one that has 4 samples is the one that is assuming periodicity. The one that is not periodic, it has an infinite number of samples. Very good. Then this we know. Okay, say something else. Yeah, so let's say that this is if I represent from minus pi to pi. What if I want to represent from 0 to 2 pi? Then if I want to represent from 0 to 2 pi, I have to take also the equivalent of this one, is this one, is for k equals 3. And now I have 0, 1, 2, and 3, and I have again 4 samples. So let's represent, we use 2 colors. So this is the way humans like to think of the Fourier transform. Let's see also a different one. And this is the way computers like to think of the Fourier transform. And how to go from one to the other, this called this FFT shift. So we do FFT shift. You go from the representation of computers that goes with k 0, 1, 2, and 3 to the representation of humans. And if you want to go from humans to computers, you do inverse FFT shift. There is something also interesting about this FFT. So what is the FFT? So what is the first F? Second is a Fourier transform. It's the first. It is the fast Fourier transform. So the fast Fourier transform is the one that makes this periodization. So periodizing makes you that you will have deltas, and then the deltas can be very quickly computed, but not the full Fourier transform in which you would have infinite values. Okay, so the first step comes from fast, okay? And it is periodization. Very good. Then this is the way computers like to think of the 2D Fourier transform. So the origin is there. So the 0, 0 frequency is in the corner, the same way as it was for 1D signals. So for 1D signals, k equals 0 is in the origin. So the origin is in the corner of the Fourier transform. And no matter if the origin is so if the size of the image is even or odd, it will the 0, 0 will be always that corner. But humans like to think of the Fourier transform with the origin in the middle. So we do the FFT shift, and then the origin moves to the middle, and the middle here it is very well defined. So here we have 8 samples. This one has 17 columns. So it has 8 columns on one side, 8 columns on the other side, and 1 column in the middle. So we have 17 samples again. But what is the origin? So what is the middle if you have 16? So you have to choose a pixel such that it has the same amount in both directions, right? It is impossible. And the reason it is impossible is because the computer, actually I made that wrong. So the computer is keeping, no, this is right. So the computer is keeping you this one, because these two are the same, sorry. Yes, wrong, sorry, because these two are the same. It is keeping this one, this one, this one, and this one. So it has one more sample on the left than samples on the right. And this is what is happening here. So the origin is in the middle, but in the middle, defined in this way: number of rows divided by 2, number of columns divided by 2. The plus 1 is a MATLAB thing. So it is at the, so if you have 16 rows, would be in row 8, starting from 0. So 0 go to 8, that is this one. Okay, so this is for the origin. Let's look the surrounding of the origin. So let's look at these. This has to do also with the following way of thinking. Okay, so let's redo it in one dimension. So let's redo it one dimension. So I had this spectrum, 5 to 5. And this is 0, this is frequency, and this is spectrum of signal. Very good. So you can report for computers, they report this one, and humans prefer thinking this one. Now, what in 2 dimensions? So in 2 dimensions, now we have the same. So we have omega x, omega y. Let me do it very long. I will do it very long. This is pi. This is minus pi. This is pi. This is minus pi. And our spectrum is in the middle. Okay. So that is our spectrum. And it is periodic with period 2 pi. So at 2 pi, we have the same spectrum. And at minus 2 pi, we have the same spectrum. And here also we have the same spectrum as there. But this is periodic everywhere. So periodic everywhere. So that means that this point also has a period, a periodic copy here. And this is 2 pi 2 pi. And also at minus 2 pi 2 pi, it extends every 2 pi in every direction. Okay, so we have said humans prefer thinking this way, but computers prefer thinking this way. Okay, so let's number the different regions of the spectrum as seen by the computer. So as seen by the computer, this is region number 1, this is region number 2, 3, and 4. And if this is 4, this is also 4, this is also 4, this is also 4, this is 4, this is 4. If this is 2, if this is 2, this is also 2, this is also 2, this is also 2, this is 2, this is 2. If this is 1, then this is also 1, this is 1, this is 1, this is 1, and this is 1. And if this one is 3, then this one is 3, this one is 3, this one is 3, this one is 3, and this one is 3. So now let's look at the spectra. So this spectra here, this spectra here. So this one here, the order is 1, 2, 3, 4, while in the computer one, it is 1, 2, 3. So 1, 2, 3, 4. You see? Any question regarding this? No? Okay, so this is what is shown here. I have used numbers, it's using colors. So when you do the Fourier transform with a computer, you have this is the origin, this is number 1, 2, 3, and 4. And when you do the FFT shift, this is 1, 2, 3, 4. It is simply where you are looking at in this spectrum. So are you looking at this period or you are looking at this period? So what are negative frequencies? So this frequency is positive. So yeah. So from here, let's say, let's use right. So for omega x, going in this direction, it is going from 0 to 2 pi. And here it continues from pi to 2 pi. Okay? So it is not that the frequencies are negative, but the 2 pi frequencies, they're the same as if you were going from 0 to minus pi. So this is low frequency again. So it is, if you, I will draw it in this. So you start with low frequency, you go to high frequency, and then you go again to low frequency, but negative. Easy? Yeah. So when you look at the spectrum in this way, you start at low frequency, then high, and then low again. And here it is the same. Low, high, and low again. If you put it this way, low frequency is here, high frequency is in the extremes.
So it's low, high,
Low,
low, high.
no. Yeah, so low, then high, and then low, and then low, high, and then low. In the other direction. No? So this is 0, pi is high frequency, and then 2 pi, but 2 pi is very low frequency again. Okay, then how does it look like for an image? It looks like this. So you take an image, you do the Fourier transform, you represent, for instance, the amplitude, and here you have the low frequency, and it is the origin, then high frequency, and then low frequency, and this in this direction it is the same. And if you do the FFT shift, then the low frequency, all low frequencies are in the middle of the image. And this is another representation, but now with numbers. Now, let's put the origin in the middle of the image, and let's consider one coefficient. Okay, so let's consider this coefficient here. So this coefficient, it has coordinate 1 to 1. So let's say that this direction may go. So it is 1 1, or this one is 1 1. This 1 minus 1. So we don't care about the so it is growing in this direction. So this one is 1 1. This one is 1 minus 1. Right. So then we have these formulas that we had before. We have these formulas to compute the wavelengths. So now we can compute the wavelength in one direction is number of columns divided by your index. In the other direction, it is the number of rows divided by your index. Okay, so let's put just one delta there, and let's see how the image looks like. Okay, so one delta there, this is the origin. So this is minus pi. Do you agree? This frequency is minus pi, and the index is minus number of rows or number of columns divided by 2. Very good. So what is the maximum frequency that we can have? If you think as humans, the maximum frequency that you can have is pi or minus pi. It's the same. So let's think of that frequency. So that, let's say it is minus pi. And it is so what is the wave associated to that frequency pi? So it is pi to the n, but this is minus 1. This minus 1 to the n. So it is a signal that is 1 minus 1, 1 minus 1. This is x of n. So x of n is this one. This is n. Then the signal goes from minus 1 to 1. It is the fastest you can have. So if you think of periodic signals that go and do it finish by, they go like this, and you make this sign faster and faster. You make it faster and faster and faster. This is the fastest you can go, right? Goes to from the maximum to the minimum is just one sample. So this is the fastest frequency in this direction, and this minus 1, 1. What is the wavelength? Okay, so the wavelength, this is the index minus c divided by 2. It is calculating the index. So what is the wavelength? So that is, it is the same as c divided by 2. So it is c divided by 2. So the c cancels and the wavelength is 2. That is, takes just 2 pixels to go from one maximum to the next maximum. Okay, what if my maximum, if I put a delta there, everything else is 0. So I put a delta there. Now I have the same effect, but now in the other direction. What if I put that one? So if I put that one, so it is minus 5. So now I will put it as an image. Put it as an image. So it will be e to the minus k, let's call it x. And e to the minus k times y. But this is minus 1 to the x times minus 1 to the y. So it is the multiplication of the two. It is the multiplication of the two, and then you have this pattern. And what if now I put the delta very, very, very close to the origin, not exactly at the origin, but just one sample away. So one sample away, it has to be something horizontal. What is the wavelength associated? So it is number of columns divided by your index, but my index is 1. So I need number of columns to reach the same maximum. So it is a wave that from maximum to maximum, it takes the number of columns of my image. So I have a single cycle here. So the index actually is the number of cycles you have. So if your index is 1 in one direction, you have one cycle. And what is my index here? In this direction? It is 0. So you have 0 cycles here. And what is my number of cycles in this direction? It is number of rows divided by 2, which makes sense again. Okay, so yeah, in the other direction, then in diagonal. So in diagonal, we have one cycle in this direction, one cycle in this direction. And the composition is the wave propagating in this direction. That is the direction of this 1, 1, 1 minus 1, whatever it is. And then in the other direction, and again, you have one cycle in X, one cycle in Y. And then you can have any number of cycles. So for instance, this one is 4, 3. So you will have 4 cycles in X, 3 cycles in Y. And let's say that my number of columns and number of rows are not the same. So the wavelengths associated, even if they have different indexes, but the wavelengths can be the same because it is number of rows divided by your index in X, number of columns divided by your index in Y. The opposite. So the wavelengths can be the same. So from one maximum to the next takes 128 pixels. And because your image is wider, you will have 4 cycles in one direction and 3 cycles in the other direction. So this is repeating the same reasoning we have done. This is rather repetitive, this part. Sometimes your wavelength is not an integer number. So that means that you're not fully having 2 exactly equivalent points. Okay, so these 2 maximum, they are not exactly the same. It's like if I have something, let's put it a one-dimensional example. So I have a signal E x of t that has period 5. So this is t equal 5. And my sampling is, let's say 2.4. So let's say that your delta t is 2.4. So you have a sample at 0. So you have a sample at 0. You have another sample at 2. Let's put some numbers here. So this is 2.5. This one is 2.5. So you have one a little bit before, another one a little bit before. So these 2 points seem more or less the same, but they are not exactly. Okay. So that is what happens if you have wavelengths that are non-integers. Okay, next. Yes, very repetitive ideas. Yeah, so some more interesting ideas. We have introduced an image, the Fourier transform, the power spectrum of that image. That we say if it is deterministic, it is the absolute value of the Fourier transform and square. And then we can have, for instance, you can do inverse Fourier transform, forward Fourier transform. So if you give me the phase and the spectrum, I can reconstruct the image and the opposite. So for any image, I can compute the power spectrum and the phase. So they contain exactly the same information. So let's think of that image. This is the amplitude. This is the phase. And now we wonder, okay, which of the two? So we have 2 images. One is the amplitude, another one is the phase. which one of the two has more information. And the way to look at that would be, okay, why don't I set all the phases to 0? I have a reconstruct, and I do the inverse Fourier transform. And let's set all the magnitudes to 1. So if I set all the phases to 0, there is no information in phase. If I set all the magnitudes to 1, there is no information in magnitude. Okay, so let's do that. This is the reconstruction forgetting about the phase. And this is the reconstruction forgetting about the magnitude. So here we don't see anything. Here we see the train. So where is the information? Most information is in the phase. That makes sense because we said the phase says where the waves should start. So should they move to the left or to the right? So let's think at the border of this table. So when I look at the table, so there must be all waves have to synchronize such that they reach the edge at the same time. So it is like the one that we had here at the beginning of the. So here, all waves have to synchronize so that they all reach the edge of the table at the same time. So the information is in the phase. So we said our ears are mostly sensitive to the amplitude, and our eyes are mostly sensitive to the phase. There is another nice illustration of this. Let me look for it very quickly. So if I look for yes, close. I go to teaching. Yeah, this one here. There is a nice illustration of that. It's the Fourier space. Here, this one. So let's say that you take two images, one duck and one cat, and you do the Fourier transform of the two. So the Fourier transform, you have complex numbers, so you have an amplitude and phase. So here somehow it is represented both. So here is the low frequency, and the color represents the phase. And here it is the same. So now you take the amplitudes from this image and the phases from that image, and you compose them. So you will have new complex numbers. And you do the inverse Fourier transform, and what you get, okay, it is not a perfect cat, but it is a cat. So that means that the visual information is in the phases. It is not in the amplitudes. The amplitudes help to get this absolutely clean, but most of the information is in the phase. There was something else that I wanted to show you. Yeah, this one here. So we have said an image is made of the sum of this kind of waves in all directions and with all frequencies. Okay, so let's look at this house. So you do the Fourier transform, and this is the amplitude. Okay, so the amplitude we recognize here in the door. We recognize this pattern that is 1 minus 1, 1 minus 1, right? So it is the fastest frequency. So that means that we need energy to represent that. So this is 0, 0. This is the maximum frequency. So we need energy. Why don't we have a single delta? And the reason you already know also from one dimension. So let's say that I have x of t. Sorry. This is t. This is x of t. You have some signal here, whatever that is, and you do the Fourier transform. Here we have Okay, good. Then you multiply this by a mask. So you put this signal and you multiply this. What is the, and you call it y, for instance. So what is the, sorry, no full transform here. By the way, these are kind of big mistakes that you do when you, if I ask you in the exam, explain me the Fourier transform, you mix Fourier space with Fourier space. So this is a big mistake. You cannot put Fourier transform with a time argument. Okay? So what is y? What is y? So it is Fourier transform J omega, because you are multiplying in time, you are convolving in Fourier space. So convolve with the Fourier transform, the mask. And this is a pulse. So if it's a pulse, then the Fourier transform of that is a sinc. So it is omega. This is modulo omega. So we will be convolving this with a delta. What we have the convolution of a delta with a mask, with a sinc. Very good. So this is for this window, for this door. Okay, what about the wall? So the wall, now the period is not 2, the period is 4, so it is half the maximum frequency. So, and now we understand that we have these ripples, because these ripples come from the convolution. Okay, what else? Then we have these windows. So we have these windows. So is one of the windows, the other window, and we have the ceiling. So what about the roof there? So the roof is special, right? Because it is not, so the white bands are bigger than the black bands. So it is periodic. So if it is periodic, you know we will need so if it is periodic, it will have, and that is actually, you may not remember the names, but this was called the fundamental frequency. Fundamental frequency. The fundamental frequency has to do with what is your period. And these are harmonics. So this is the first harmonic, second harmonic, third harmonic. So you have the fundamental period, that is this one. You have the fundamental period and harmonics. And this is for these kind of houses. For an image, it is the same, exactly the same, only that we don't see the waves here, right? But it is exactly the same meaning, exactly the same. Any question? Okay, so the Fourier transform is difficult. And what it brings you is another way of looking at images. So now you look at images, but now based on the waves that made those images. You have low frequencies, or if you want to do, for instance, a low pass filter. So for instance, here I have this image, I do a Fourier transform, I keep only the Fourier components here, all the rest I set to 0, and then this is what I recover. So what have I lost? The very, very low frequency. So the very, very low frequency is this one. So you have to compose this image into 2 parts. One that is very low frequency, another one that has middle frequency. And this one is the addition of these two. Very good. Any question?